Okay, welcome to week 10 in review. And the plan for today is to talk about Nyquist stability. So let's review the major setup. So the idea is the following. We're always talking about feedback unity. So we're talking about this overall transfer function. And PK is called the loop, sometimes called the open loop transfer function. It's as if we cut this feedback leading back. So this is called the loop function. And note that the closed loop transfer function, PK over 1 plus PK, is written as L over 1 plus L. Again, this is just standard notation that you'll find in pretty much any textbook. So the idea is the following, and it's used in the same principle goes for Bode plots, etc. That we can get a lot of information by looking at what happens to L of I omega, where it maps just the frequency. Now we're not going to talk about where this theorem came from in this review. We went over that in detail in class. So we'll just go over what the main theorem of Nyquist stability says. So it says the following. First, suppose that L has no poles on the imaginary axis. It may have poles in the right half plane if the open loop is unstable. It may have poles in the left half plane. But suppose for now that it has no poles on the imaginary axis. Then let gamma be this curve that I'm drawing. It's an infinite curve. And note that again, it's actually on the imaginary axis. I'm just drawing it like this for clarity. That has radius r, which we're going to take as going to infinity. So this curve, which we'll call gamma, which is oriented in the clockwise fashion, encloses the entire right half plane. The right half plane as r goes to infinity. There's no part of the right half plane that's not contained inside of gamma, of the open right half plane that's not contained inside of gamma. Now let's look at where L maps each point on this curve. So again, remember the concept that we talked about extensively in class is that for every point on this curve is a complex number, and L of that is also a complex number. So for example, this point might be the point 3i. L of 3i is also some complex number. It has a real part and an imaginary part, and therefore we could plot that wherever it happens to fall. And the idea is that if we do that for every single point on this curve, then we may map out some kind of curve. Perhaps it will look something like this. The Nyquist stability theorem says, let's let P equal the number of poles of L in the right half plane, or rather, to be precise, enclosed by the curve gamma. Let's let Wn equal the number of clockwise encirclements of -1 by the curve L of gamma. In other words, this dashed line here is L of gamma. So, for example, if this is -1 and our curve looks like this and it's oriented in this way, then Wn would equal positive 2. As another example, if again, what I'm drawing is L of gamma. If L of gamma it were to look something like this, and minus 1 is out here, and the curve is oriented like that, then Wn would equal 0. If if gamma looks like this, and minus 1 is in here, then Wn is equal to minus 1. So we see various different possibilities. So this is P, this is Wn. So Nyquist stability says the following: the number of closed loop poles inside the right half plane. This is again what determines stability. So when I mean closed loop poles, I mean of poles of pk over 1 plus pk. This is equal to Wn plus P. So it's best to illustrate this with an example. So let's do a problem similar to the ones that you saw on the homework. So let's suppose that L of s is equal to 3 minus 4s over s squared plus 6s. We'd like to plot it. Note that there is an issue here. We have a pole on the imaginary axis. So this is different than what the assumption of the theorem says. So we need a key modification. We need to alter gamma so that it satisfies two things. First, so that there is no pole on the curve gamma, but we also want to maintain the property that gamma encloses the right half plane and nothing more, and nothing from the left half plane. How can we accomplish this? Well, we modify gamma by simply avoiding, in an infinitesimal way, the pole at 0. So, for example, we could let gamma be this curve, where again, the big radius, r, is going to infinity, and this little radius, r, is going to 0. We could also draw it in a different way, where we avoid the pole going to the left. This r is still going to infinity, and this little r is going to 0. So note that both of these curves satisfy the two properties that they enclose everything in the open right half plane, nothing from the open left half plane, and they avoid the pole. They avoid the open pole. So for now, let's take this example. Let's let this be gamma, and let's label the different parts of the curve: gamma 1, gamma 2, gamma 3, and this little circle gamma 4. And let's see where it maps by L of s. Well, as you'll notice, and as we've discussed in class, this outer curve, because the numerator has degree smaller, strictly smaller than the denominator, this maps to 0 as r goes to infinity. So really what gives us most of the information is mapping the imaginary axis. So the key thing to do is, from L of s, first compute what L of I omega is. L of s is up top, so let me rewrite it here. It's equal to 3 minus 4s over s squared plus 6s. So L of I omega is equal to 3 minus 4I omega over minus omega squared plus 6I omega. We need to multiply by 1 by the complex conjugate in order to write this, separate the real and imaginary part. And a little bit of computation will show you that this is equal to minus 27 omega squared over omega to the fourth plus 36 omega squared, that's the real part, plus I times 4 omega cubed minus 18 omega over the same denominator, of course, omega to the fourth plus 36 omega squared. One key thing to note is that the imaginary part has all odd terms of omega in the numerator, while the real part has only even terms. In other words, the real part of L of I omega equals the real part of L of minus I omega, whereas the imaginary part of L of I omega is equal to minus the imaginary part of L of minus I omega. So what this means is that the image of gamma 1 is just the mirror image of gamma 3 flipped across the real axis. Okay, so let's so we can plot a few values of omega and L of I omega. So for example, we can plot omega equals 1, omega equals 2. Plotting omega equals 1, we'll find that L of I omega is equal to minus 27 over 37 is the real part, plus I times minus 14 over 37. Plotting 2 would give us the real part is, again, negative. In fact, you'll see it's always negative. 108 over 160 plus I times minus 4 over 160. And if we were to plot more points, we would find that plotting the real part, the image, oops, let me redo that, would give us this. So what I've plotted is the image, so L of gamma 1. Now, from what we just said, the image of gamma 2, of gamma 3, must be the mirror image, L of gamma 3. And this point at 0 is the image of gamma 2, which is that big loop out at infinity. So all we have left is to plot L of gamma 2. Now we already have the orientation here. And it's not difficult to check that it comes out in this direction. So for example, if you look at L of some very small number, for R very small, we see that this is equal to 3 minus 4R over R squared plus 6R, which is roughly equal to 3 over 6R, which is some very huge positive number way out here. And this is how I got what the orientation of this curve is. So let's see what Nyquist gives us. Well, we have the number of poles in the right half plane. Remember, let me write it again since we've scrolled now. L is equal to 3 minus 4s over s squared plus 6s. So we have poles at 0 and at minus 6. And because of how we oriented gamma, P is equal to 0. There are no poles inside of gamma. If we had drawn it differently and avoided the pole at the origin going to the left, then P would equal 1. What about Wn? Well, we don't know. We need to, so why don't we know? Because we need to know where is minus 1 in relationship to this point. Where is -1 compared to this point? So let's do that. Let's compute that point. What is special about that point that allows us to compute it? Well, notice that it has no imaginary term. It's a point at which the imaginary term is equal to 0. So remember that L of I omega is equal to minus 27 omega squared over omega to the fourth plus 36 omega squared, and the imaginary term is 4 omega cubed minus 18 omega over the same denominator, omega to the fourth plus 36 omega squared. So the point at which the imaginary part vanishes, to compute the critical omega, this is where 4 omega cubed minus 18 omega equals 0, and we can solve for this quite easily. This is the same as writing 2 omega times 2 omega squared minus 9 is equal to 0, or omega is equal to plus or minus, and note that it makes complete sense that we should have two symmetric roots, the square root of 4.5. And if we evaluate L of I omega critical, either positive or negative, it doesn't matter, because the real term is going to be even. In other words, it's insensitive to the sign, and the imaginary term is equal to 0. We find that this is equal to minus 27 divided by 40.5. My calculation was correct. In other words, redrawing, we find that the Nyquist plot is equal to this, and this point here is equal to a little bit more than 1/2. So we can draw -1 out here. This value is that point. So that means that Wn is equal to 0. And the conclusion is that the system is closed loop, number of closed loop poles in the right half plane is equal to 0, hence we're stable. And as an exercise, check this using Ruth-Hurwitz. Now, what are the kind of things that I'm interested in here, and what can we talk about that's more interesting than what we could do with Ruth-Hurwitz? And that's different kinds of stability and robustness. So note the picture again that we have. It looks something like this. Oriented oppositely from how I drew it. Oriented like this. There are several, and we know that -1 is out here. So suppose that our true L were something like A times alpha times the L that we used to draw it. How big can alpha be? So what we can see from above is that we are stable as long as alpha is smaller than, any guesses? (40.5 over 27). And the reason is that that is what's needed in order to keep that -1 on the outside. More interesting is what's called the phase margin. So suppose that our true L were equal to some phase times the L that we used to draw. What would that do? That would rotate the entire picture. How much can we rotate before we possibly incur some encirclements of -1? Well, in order to compute that, if we draw the unit circle, we see that this point here that I'm circling, it's these 2 points that would be the first to cross over -1, and the first that would cause some kind of encirclement of -1. Therefore, this angle, this is the critical angle. And what this shows is that we are stable, that as long as the rotation is strictly less than the critical angle, the negative phi c, and strictly greater than minus phi c, and strictly less than positive, then L true is also then the closed loop system with L true is also stable. What else can we do? The so-called stability margin cares about the setting where we have additive perturbation. L true is equal to L plus some perturbation delta. And the question is, if I have a bound on delta of I omega, how big can delta be before let's phrase it differently. How small must delta be in order for us to be able to guarantee stability? And the key is without knowing anything else about delta other than its size. In other words, the system could be incredibly complicated, have loops and turns and twists. Not know about delta. So let's draw the picture again. So what we're saying is that this is the point, these are points that we drew with L, but in fact, here's my minus 1 here, but in fact, the point that I drew here might have been at any radius delta. So this blue line here, it could have been doing anything crazy as long as it stayed inside that circle. And similarly as we go across. And we can see from this picture that the key point, delta, if we don't know anything else, it must be closer than the minimum distance. It must be smaller than the minimum distance. So delta must be smaller than the minimum distance from L to L of gamma, I should say, to the point minus 1. Another way to write this is that the distance between L of I omega and minus 1, so L of I omega minus 1, which is plus 1, has to be bigger than delta of I omega for every omega. And this guarantees stability. This condition guarantees stability. And this is a very powerful idea that cannot be, we can't do anything even approaching this using other methods that we've talked about in this class. The small gain theorem, which we'll talk about next week, is a generalization of this powerful idea.